Hello everyone. Today I'll be presenting a paper titled Security Games for Vehicular Networks. This paper delves into the realm of vehicular ad hoc networks, or VA-nets, a rapidly emerging field that aims to improve transportation security, reliability, and management. The authors of this paper tackled the challenge of securing these networks by applying game theory, a mathematical model used to analyze strategic interactions between different players. Our discussion will revolve around the problem statement, why game theory is a potential solution, the game concepts used in the paper, the technical details of the proposed solution, and the scope for future improvements in this research. Let's explore how game theory can help us secure vehicle networks. The problem statement of the paper is centered around the security and management of vehicular ad hoc networks. VA-nets, which enable vehicle-to-vehicle and vehicle-to-infrastructure communications, are an emerging research field aiming to improve transportation security, reliability, and management. The paper investigates network connectivity issues and mappings of car networks to the underlying road topology. The authors aim to locate hotspots in vehicular networks to determine the most vulnerable points for jamming and to optimize the placement of roadside units. They also use game theoretic analysis to investigate the effects of possible malicious users on the system for increased reliability and better management of resources. Now let's explore why game theory is a potential solution tool for this problem. Game theory is a potential solution tool for the problem of securing vehicular networks due to its ability to model and analyze strategic interactions between different players, in this case, the attackers and defenders of the network. Zero-sum game. When both players know the payoff matrices of each other, a classical zero-sum game can be played to inform the attack and defense strategies. This game is particularly useful when the payoffs are known precisely. Fuzzy game. When the payoffs are only known approximately but not exactly, a fuzzy game formulation allows for definitions of range and tolerance of imprecision. This game can be useful for interaction with humans as it makes it easier to communicate when people can express estimations in vague terms. Another benefit of fuzzy game formulations is that fuzzy linear programming problems save time in comparison to using Monte Carlo techniques. Fictitious play learning. When the players do not know each other's strategy, they can learn to improve their strategies by fictitious play. This approach is useful when the players have incomplete knowledge and need to adapt their strategies over time. These game theoretic models provide a systematic way to analyze and optimize the placement of roadside units, assess the importance of road segments in the context of security and traffic flow, and investigate the effects of possible malicious users on the system for increased reliability and better management of resources. Now, let's explore the game concepts, players, strategies, and utilities in this paper. Players. The players in this game are the attacker and the defender. the attacker is interested in disrupting the network by physically jamming the wireless signal in a given region of the map. The defender can be a fixed or mobile unit able to detect and remove a jammer, such as a police car or a network stakeholder. Other examples include a designer, a city planner, or law enforcement. Strategies. The action space of the games consists of all the squares the map is divided into. The attacker chooses one square in the pure strategy or several squares in the mixed strategy with a probability to jam the network. The defender chooses one or more squares to be stationed at a road segment to defend. The strategies can be dynamically allocated. For example, sending police cars to selected squares in reaction to learning about attacks. Utilities. The utilities are represented by the payoff matrix. The values depict the payoff of a particular attacker-defender position. Example, proportional to the chosen metric betweenness centrality if the attacker chooses the square. The payoff matrix in its simplest form consists of columns of squares for the attacker to choose and rows of squares for the defender. The players either have complete knowledge of the payoff matrix in the zero-sum game formulation, or at least an approximation thereof in the fuzzy game formulation. Now, let's understand the technical details or proposed solutions. The technical details and proposed solutions involve the application of different game theoretic models to the domain of vehicular networks. The authors in this paper first developed quantitative measures for assessing the importance of road segments in the context of security and traffic flow. They then used game theoretical analysis to investigate the effects of possible malicious users on the system for increased reliability and better management of resources. The authors consider an attacker interested in disrupting the network by physically jamming the wireless signal in a given region of the map. The defender, which can be a fixed or mobile unit, is able to detect and remove a jammer. The action space of the games consists of all the squares the map is divided into. The attacker chooses one square in the pure strategy or several squares in the mixed strategy with a probability to jam the network. The defender chooses one or more squares to be stationed at a road segment to defend. The authors applied different game theoretic models such as simple zero-sum static games, fuzzy games, and stochastic fictitious play learning games. The choice of game depends on the knowledge the players have about the utility derived from attacks and defenses. For example, when both players know the payoff matrices of each other, a classical zero-sum game can be played. When the payoffs are only known approximately, but not exactly, a fuzzy game formulation allows for definitions of range and tolerance of imprecision. When the players do not know each other's strategy, they can learn to improve their strategies by fictitious play. The authors also discuss the use of a simulator for ease of use while providing realistic vehicular traces. They have also used a multi-agent microscopic traffic simulator, which provides large-scale traces of Zurich for a 24-hour period. Now, moving on, let's analyze the scope of improvement. The scope of improvement in the paper is outlined in the future work section of the paper. The authors suggest the following areas for further research: investigating suitable fuzzy membership functions. The authors use the trapeze membership function to express the payoff metrics in fuzzy terms in this paper. However, they suggest that investigating other suitable fuzzy membership functions could be beneficial for future work. Another scope of improvement that's suggested in this paper is exploring other learning algorithms. The authors use fictitious play as a learning algorithm in this paper. They suggest that exploring other learning algorithms could be an area of improvement for future work. Furthermore, the authors suggest that developing a more detailed attacker model and assessing its effects in different scenarios could be beneficial for future work. This could help in understanding the attacker's strategies and behaviors in a more comprehensive way. Considering collusion, the authors suggest that taking into account collusion, where multiple attackers may work together to disrupt the network, could be an area of improvement for future research. This could help in understanding and mitigating more complex threats to vehicular networks. Lastly, the authors suggest that in the dynamic case, roadside unit placement could be adaptive to conditions in the vehicular network, such as traffic patterns or attacks detected. This could help in optimizing the placement of roadside units for increased network security. In conclusion, the paper Security Games for Vehicular Networks provides a compelling approach to securing vehicular networks using game theory. It offers a unique perspective on how strategic interactions between attackers and defenders can be modeled and analyzed to enhance network security. The author's application of different game theoretic models, including zero-sum games, fuzzy games, and fictitious play, provides a robust framework for understanding and mitigating threats to these networks. However, as with any research, there is room for improvement and further exploration. Future work could focus on investigating suitable fuzzy membership functions, exploring other learning algorithms, developing a more detailed attacker model, considering collusion, and adaptive placement of roadside units. This paper serves as a stepping stone towards a more secure and reliable future for vehicular networks. I hope this presentation has provided you with a deeper understanding of the application of game theory in securing vehicular networks. Thank you for your time.